in template-based fuzzers, what you do is that you take sample files or sample communication traffic and you build the protocol model from those. So instead of randomly mutating those, you actually build and deduct the protocol structures from the real traffic. So it's extremely quick to develop because it's very general purpose. You only have one fuzzing framework and it will automatically build you fuzzers for any protocol out there. But it's quite slow to run because it cannot find all the protocol details in the packets, and it cannot find all the different aspects from the traffic. So it often takes time to generate, or what can also happen is that you need more test cases than in a specification-based fuzzer. And when you do template-based fuzzing, editing those test cases that you generate, editing those protocol models that you create often requires quite deep protocol know-how. So you basically need to take the protocol specification anyways and compare what was in the deducted model from the traffic and see what type of elements, what kind of data is supposed to be in those elements, where the length values are, and so on and so on. But the good benefit for template-based fuzzer is that it's very good actually for using in quickly identifying, for example, doing patch verification around known vulnerabilities or different use cases that you can capture from the network. Specification-based fuzzer, on the other hand, aims to do full test coverage. So it means that instead of taking samples of traffic and sample use cases from the network, it actually implements all the specifications for those protocols, and therefore it is extremely powerful in testing the areas that you almost never see on the network. So for example, all the optional elements or vendor proprietary extensions and such, you cannot often see those in the network, or it's very hard to find those samples. And in those cases, a specification-based fuzzer can actually get better test coverage in much more optimized test execution time. And as everything is based on a specification, it's very easy to repeat those same tests in different environments. So if you take a capture in one environment, you cannot necessarily run it on a different environment. But when you take a specification-based fuzzer, it adapts to the changing environment around it. And as you optimize test cases, you get much more effective test execution times and also much more optimized test efficiency. So tests are able to find more weaknesses than with template-based fuzzers. And as the test cases are built from the specifications, it's also possible to generate documentation for every single test case. Even if you have millions and millions of test cases, every single test case can still be fully documented. So you have reasons for each test case, and therefore you can do automated risk assessment for all the found weaknesses as well. And that makes it much easier to edit and add new test cases as well, because you have test cases and you can easily see what was already tested and if you need to add test cases in the first place at all. So after you have those fuzzing tools, the remediation aspect then actually relies quite often into traditional security technologies like IDS or IPS. So for example, intrusion prevention systems are trying to detect failures that are known by the security vendors. But if you can train your IPS systems to catch the weaknesses that are relevant to you, you can actually make best usage out of these products. So one of the shortcomings of IPS systems is that when you get the new fingerprints or new rule sets, they are already outdated because you have already fixed those issues that it's trying to detect. Whereas if you have 0 days or weaknesses that you would like them to block, unfortunately the security vendor is not aware of those weaknesses yet. So it's very hard to, for example, even reveal the details of those weaknesses to them in order to protect yourself. So in the end, zero-day remediation in the IDS IPS space is focused on knowing what to block and only block those, because you don't need to have all those thousands and thousands of fingerprints for systems that you are never even going to use, but you need to focus on blocking and protecting the systems that you are really using. So IDS systems, at least recently, have been identified to have a major shortcoming in the amount of fingerprints that they can handle. So, for example, some IDS systems, when you start exceeding a couple of thousands or tens of thousands of fingerprints, it actually starts to hop down or slow down the networks and the capability of processing the traffic. So in those cases, the IDS vendors automatically start adapting the rule sets, and you don't necessarily know which rules are active and which rules are not. Many of those fingerprints that are active might actually be completely irrelevant to your specific production system. So if you could refine and influence the fingerprints that are in use, or if you can build your own fingerprint library, then actually you get much better benefit from this system. So in the demo that I will be showing, we are using Snort IDS as a demonstration environment. And first we'll use a voice over IP rule set. So it uses the standard Snort voice over IP detection rules. And then based on the discoveries that we do with fuzzing tools, we modify those rules to detect the actual weaknesses in the system in order to block those attacks. And the last step that I will then go on presenting in the demonstration is looking at patch verification aspects for known issues. So a very common problem with patches has been that the patches are not necessarily the best possible quality. In worst cases, for example, if a patch is supposed to fix a buffer overflow problem, the programmers, when they actually implemented the patch, they just increased the size of the buffer. So in a fuzzer, the next test case actually would still crash the product, but it's actually very hard to verify that as a consumer of software. And it's even hard to verify for the vendors themselves. So they don't know what kind of updates their programmers do when they are in this crisis management process. So most bugs, most weaknesses, most of the patches are released in a hurry. So the vulnerability data that you get from different vendors' advisories and such is not necessarily enough for testing for the bug and different variants of that bug. And also your own configuration can affect the results. So the different sample exploit that might be provided by some of these advisories might not work in your setup at all. A slight modification to the exploit, proof of concept exploit, could actually verify that the patch didn't work at all in your specific environment. So when you combine vulnerability feed data with traffic capture fuzzing, template-based fuzzers, you can do all these things. You can do testing of the original vulnerable software and verify that you actually do have that weakness. You can then also verify the patches issued by the vendors and also test around those weaknesses to verify that they didn't actually make new mistakes by mistake while introducing the corrections. And then with exactly the same techniques, you can also test your own IDS rules and your firewalls that you are actually protected against these attacks, and that your auditing techniques will detect these attacks as well. So even being able to go back to your system event files or log files and see that these attacks will trigger some type of alerts, and even if a system is crashing, you will be able to detect that it was crashing and it was exploited, because a silent exploit is often the worst nightmare for system administrators, when something was exploited but there was no trace of it in the log file.